Okay, so we're now going to go through solving quadratic equations that have complex roots. Right, so a quadratic always has two roots. They might both be real roots, they might both be complex roots. Okay, so let's look at the following. Remember your minus b formula. Okay, so to solve a quadratic, you're going to use your minus b formula. And if the discriminant, and remember the discriminant is the part underneath the square root, if the discriminant ends up being a negative number, you know you're going to end up with complex solutions. Okay, so the discriminant would have to be a negative number in order for those two roots to end up being complex. Alright, so let's look at this first example. Solve the quadratic equation z squared minus 6z plus 13 is equal to 0 and show the roots on an Argand diagram. Okay, so just go off and do your minus b formula. So a is 1, b is minus 6 and c is 13. Sub into the minus b formula. Okay, use your knowledge that the root of minus 1 is I. Okay, so you're breaking up the root of minus 16 there to be root 16 by root minus 1. The root of 16 is 4. The root of minus 1 is I. Okay, tidying that up, split up the division by a real number. So it's going to be 6 over 2 plus or minus 4i divided by 2. And that ends up being 3 plus or minus 2i. So they are the two roots of that quadratic. So one is 3 plus 2i and the other is 3 minus 2i. So you'll note that one of the roots, so z is equal to 3 plus 2i, z conjugate happens to be the other root. Okay, and that comes from the conjugate root theorem. The only reason that applies is because if we look back at our quadratic at the very beginning, it was z squared minus 6z plus 13. All the coefficients there are real numbers. So like the coefficient of z squared is 1, the coefficient of z is minus 6. The fact that the coefficients are real numbers would tell me that if I get one of the roots and it's complex, well then the conjugate of that root would also be a root of the function itself. Okay, so we'll get on to that more a little later. Alright, so plot the 2 points. So there's one of the coordinates, one of the roots, z, and there's the conjugate. Alright, so we plotted the two roots and you can see the conjugate, they're a reflection of each other through the real axis. Okay, so next we're going to look at forming a quadratic once you've been given the roots. Now we've done this already when we did algebra. Okay, so we're going to go with the same procedure. So there's two methods. This is the first method. Okay, if they have given you the two roots, well then you know the two factors straight away. Okay, so let z equal both roots. Step 2 then, get the factors. So just bring everything over the equals and you'll have z minus or plus, whichever, all now equal to 0. You now have the two factors. Then you would multiply both of the factors together and you'll get out a quadratic. Okay, so that's method 1. Alternatively, you could go with method 2. So you could use this formula for getting out the roots of quadratics. So z squared plus the sum of the roots times z plus the product of the roots all equal to 0. Okay, so you could go with that approach as well if you wanted to. Doesn't really make a difference which one you go with. Sometimes the second approach is shorter, quicker. I just tend to always go with method 1 just because it makes more sense. Whereas this is a formula you have to learn off because it's not in the log tables. Whereas this method makes more sense. If you're given the roots, work backwards to get the factors, work backwards to multiply them out and get back the quadratic. Okay, but it can be a little bit cumbersome. Okay, so let's look at the first example here. Okay, so form a quadratic equation from the following pairs of roots, giving your answer in the form of az squared plus bz plus c is equal to 0, where a, b and c are all elements of integers. So the roots are 2 plus and minus 3i. So I'm going to go with the first method. Okay, so I've been given the roots, right? So z is either equal to 2 plus 3i or 2 minus 3i. Step 2, well, if I know the roots, I know the factors. Bring everything over the equals. So it's going to be z minus 2 minus 3i for my first factor, or z minus 2 plus 3i equal to 0, my second factor. Now, put both factors into brackets, and in step 3, multiply them out. Okay, so we're just multiplying them out, split the brackets. Now, there's 3 terms, technically, in each of the brackets. So it's going to be z in the first bracket multiplied by all of the second bracket, minus 2 in the first bracket multiplied by all of the second bracket, and minus 3i in the first bracket multiplied by all of the second bracket. Okay, so just watch your multiplication. Z by z is z squared, z by minus 2 is minus 2z, z by 3i is plus 3iz. The order in which you write that is fine, you could write it as 3zi if you want. Minus 2 times z is minus 2z, minus 2 times minus 2 is plus 4. Minus 2 times plus 3i is minus 6i. Minus 3i times z is minus 3iz, or minus 3zi, whichever way you want to write it. Minus 3i by minus 2 is plus 6i, and minus 3i by plus 3i is minus 9i squared. Now remember what I squared is. I squared is minus 1. So we're going to start tidying this up. Okay, so you'll see certain things will start to cancel, right? So I've got a plus 3iz here. I've got a minus 3iz, so they'd actually cancel each other out. I also have a minus 6i and a plus 6i, so they'd cancel each other out. So I'm then left with minus 2z, which is minus 4z. And I have a plus 4 and minus 9i squared. So that's the same as plus 4 minus 9 times minus 1. Minus 9 times minus 1 is plus 9. So that's 4 plus 9, which is 13. So I have now gotten back the quadratic. So that quadratic, z squared minus 4z plus 13 is equal to 0. That quadratic has the two roots, 2 plus or minus 3i. Okay, so that's using method 1. If you want to do the alternative method, method 2, put down the formula, which you have to learn off by heart. Z squared plus the sum of the roots times z plus the product of the roots, all equal to 0. So remember what the roots were. They were 2 plus 3i and 2 minus 3i. So it will be z squared plus the sum of the roots times z. So you're adding the two roots. Remember, keep real with real and imaginary with imaginary. So 2 plus 2, okay? And then 3i minus 3i, and there's a plus in the middle. 2 plus 2 gives you a 4, and they cancel each other out. 3i minus 3i is gone. So you're left with 4 in that big square bracket multiplied by z, so 4z. Then working with the product of the roots. So 2 plus 3i multiplied by 2 minus 3i. Split the brackets and multiply it out. You'll end up with this. The i's cancel. You're left with 4, and a minus 9 by I squared is minus 1, so that's plus 9. 4 plus 9 is 13. Okay, so if you want to go with method 2, that's fine. But just make sure you know one of the two methods anyway to do it out. Okay, next, in your books on page 297, I want you to do the following questions. So question 3, question 5, 8, 9. In 9, multiply out the right hand side and bring everything over to get a quadratic. Question 11, part 5 and part 6. Question 12, form a quadratic with each pair of roots and giving your answer in the form of az squared plus bz plus c, where a, b and c are all integers. Okay, so you're doing part 6 there and part 7. Now they're giving it in fractions, so they're the roots. So when you're given a root, you get the factor. If you're going to go with that method, right, you're getting the factors. But I don't want to deal with fractions. It's very difficult dealing with fractions. So when you have z is equal to each of these, get rid of fractions, okay, multiply across by the lowest common multiple. All right, get it out of fractions first. That's my hint there for question 12. Question 14. And again, in 14, right, so first of all, that's division of complex numbers. Write it as in rectangular form, grand. So you're multiplying above and below by the conjugate. Hence, so using that, using whatever answer you get there, show that that is a root of that. If something is a root of something, it should sub into it and solve it, shouldn't it? So you'll go off and sub in and you should get 0 equals 0. Part 3 then says, find the other root. Well, if you know that whatever you get here for this, if that is a root of that, and remember what I said already about the conjugate root theorem? Well, the conjugate should also be a root. So you could just sub in the conjugate. Alternatively though, if you know that whatever you get for this is a root of that, if you know the root, you know the factor. And if something is a factor of something, it should divide into it evenly with a remainder of 0. So you could divide the factor, long division. Okay, you could divide in the factor into that, and the other factor up on top would be the other factor. And if you know the factor, you know the root. Okay, so you go that method as well. So pause the video, go and do those questions, and then come back and watch the solutions. Okay, so question 3. Evaluate the following. 1 minus 2i to be squared. So it's the bracket by the bracket. Square out the bracket and you should end up with minus 3 minus 4i as your answer. Part 2. Minus 2, a bracket 1 minus 2i. So multiply into the bracket by the minus 2. You should get minus 2 plus 4i. Hence, show that 1 minus 2i is a root of that equation. Z squared minus 2z plus 5. If it's a root of it, it should sub into it and solve it. Okay, so 1 minus 2i is your z value. So you're subbing that everywhere there is a z. Okay. So again, 1 minus 2i, square the bracket, but we've already done that in part 1. So the answer to that worked out to be this, minus 3 minus 4i. So the work is already done. Okay, minus 2 times that, which we've already done in part 2, which is minus 2 plus 4i. And then bring down your plus 5. And then just group real with real and imaginary with imaginary. The 5's cancel and the 4i's cancel, so you get 0. Therefore, my left-hand side is equal to 0, my right-hand side was 0. So 1 minus 2i is a root of that quadratic. Question 5. Solve the quadratic equation and give your answer in the form of a plus bi. Well, straight away that's telling you they're going to be complex. So use your minus b formula. Okay, and tidy it up, split it up, it'll be 8 over 2 plus or minus 2i over 2, which becomes 4 plus and minus I. Question 8, same thing again. Solve the quadratic and give your answer in rectangular form. So again, divide it up, it's 12 over 2 plus or minus 4i over 2. You should get out 6 plus or minus 2i. Question 9. Find the roots of the following quadratic. So, as I said, multiply out the right-hand side, okay, and then bring everything over to the left-hand side. So when you do that, you should end up with this quadratic z squared plus 10z plus 34 equals 0. Use your minus b formula, and you should be able to get out minus 5 plus or minus 3i as your solution. Question 11. Part 5. So again, it wants us to form a quadratic equation whose roots are 8 plus or minus I. So again, I'm doing method 1. If I know the roots, I know the factors. Okay, so I'm bringing over the 8 plus I onto the other side. So I'll get z minus 8 minus I. That's one factor. And bring over the 8 minus I onto the other side, and I'll get z minus 8 plus I. So there are my two factors. Multiply them together, okay, and split the brackets. So when I split the brackets, be careful with all of your multiplication. You should get z squared minus 8z plus zi minus 8z plus 64 minus 8i minus zi plus 8i minus I squared all equal to 0. You'll see then things start to cancel. I've got a plus zi here and I've got a minus zi there, so they cancel. I've got minus 8i and plus 8i, so they cancel. And remember, I squared is minus 1. So your next line then, minus 8z and minus 8z is minus 16z, plus 64 minus, and this was your I squared, which is minus 1. Watch your signs. So minus by minus is a plus 1, so 64 plus 1 is 65. So the quadratic whose roots are 8 plus or minus I is z squared minus 16z plus 65 equal to 0. Part 6 of question 11. Minus 5 plus or minus 12i are the two roots. Okay, so if they're my roots, work backwards, then they're my factors. Bring everything over to the equals, change signs. I'm now multiplying those two factors together, so you're splitting the brackets. Alright, watch your signs now when you're multiplying things out. So the next line then you should get a z squared plus 5z plus 12iz plus 5z plus 25 plus 60i minus 12iz minus 60i minus 144i squared equal to 0. Again, look at what is cancelling. I've got a plus 12iz and I've got a minus 12iz, so they're gone. I've got minus or plus 60i and minus 60i, so they're gone. And remember, I squared is minus 1. So your next line then, it's going to be plus 5z is plus 10z. 25 plus the minus 144 times minus 1. Okay, which is going to end up being plus 144. So 25 plus 144 is 169. So z squared plus 10z plus 169 equal to 0 is the quadratic whose roots are minus 5 plus or minus 12i. Question 12. Part 6. So the roots are minus 2/5 plus or minus 3/10 of I. Okay, so I'm starting off with the roots. Now straight away I said get rid of fractions because it's too hard to deal with fractions. So the first thing I did was I multiplied across by 10 because that's the lowest common denominator between 5 and 10, or lowest common multiple, whichever you want to call it. So multiply across by 10. I'll then be left with 10z. Okay, 5 into 10 will go twice, and 2 by minus 2 is minus 4. 10 into 10 goes once, you're left with 3i. So I've now got 10z minus is equal to minus 4 plus 3i. Bring everything over the equals then to get the factor. So it's 10z plus 4 minus 3i is now equal to 0. Okay. Initially, you may have brought over the minus 2/5 and the plus 3/10 I initially, and then you might have multiplied across by 10. That's fine. You'll still get that same factor there. Same on the other side. Okay, multiply across by 10 to get rid of the fractions. You end up with 10z is equal to minus 4 minus 3i. Bring everything over the equals then and you have your factor. I'm now multiplying both of those factors together. So split the brackets. Alright, so it's going to be 10z by the second bracket plus 4 by the second bracket minus 3i by the second bracket, all equal to 0. Multiply it out and watch your multiplication and watch your signs. You'll end up with 100z squared plus 40z plus 30zi plus 40z plus 16 plus 12i minus 30zi minus 12i minus 9i squared equals 0. The 30zi cancels with minus 30zi, 12i cancels with minus 12i. So then you're left with the next line. So it's going to be 100z squared plus 80z plus 16 minus 9 times, remember I squared is minus 1. You'll end up with 100z squared plus 80z plus 25 equals 0. And again, 5 is common the whole way across, so I'm going to divide across by 5. And I'll get 20z squared plus 16z plus 5 is equal to 0. Part 7 of question 12. Same thing again. Okay, there were the roots. So again, I'm getting rid of the fractions. So the lowest common multiple there is 20. Okay, the lowest common multiple between 4 and 5 is 20. So I'm multiplying across by 20. So I'll get 20z is equal to 4 into 20 goes 5 times, and 5 by minus 3 is minus 15. 5 into 20 goes 4 times, 4 3s are 12, so I get 12i. Now bring everything over the equals. So I get the factor 20z plus 15 minus 12i. Do the same with the other root. Multiply across by 20, tidy it up. Bring everything over to the left-hand side, and you get 20z plus 15 plus 12i is equal to 0. You're now splitting the brackets and multiplying those two factors together. Okay, so you should end up with 400z squared plus 300z plus 240iz plus 300z plus 225 plus 180i minus 240iz minus 180i minus 144i squared equal to 0. Okay, things start to cancel. You end up with the next line, 400z squared plus 600z plus 225 minus 144 by minus 1, which is plus 144, and you end up with 369. That can't be simplified, so I'm leaving it as 400z squared plus 600z plus 369 equal to 0. Question 14. Write 14 plus 5i all over 4 minus i as x plus yi. So basically write it in rectangular form. So we're multiplying above and below by the conjugate. So the conjugate of that denominator is 4 plus I all over 4 plus I. Watch your multiplication. So it's top by top, bottom by bottom. Split the brackets, multiply it out. 17 goes into all three terms. So you should be left with 3 plus 2i. So that's your complex number for part 1. Part 2 said hence, so using that, show that that is a root of z squared minus 6z plus 13 equals 0. So to show something is a root of it, it should divide into it, or it should sub into it and solve it. So we're subbing into it. So z squared minus 6 times z plus 13, and that should equal 0. So you need to square out the bracket. So it's the bracket by the bracket, and when you do that, you end up with 9 plus 12i plus 4i squared. Then you're multiplying minus 6 into that bracket, and you get minus 18 minus 12i, and then bring down your plus 13, all equal to 0. Tidying things up then, 12i and minus 12i cancel. I squared is minus 1, so that's going to be 4 times minus 1, which is actually minus 4. So it's 9 minus 4 minus the 18 plus the 13. Okay, all of that goes to a 0, and they cancelled anyway, so you get 0 plus 0i, which is 0. Therefore, 3 plus 2i subbed into the quadratic equation exactly. Okay, I got 0 equals 0, so therefore it is a root. Part 3. Find the other root of that complex, or of that quadratic. Well, the fact that I know 3 plus 2i is a root, based on the conjugate root theorem, all the values in that quadratic, all the coefficients were real numbers. It was z squared minus 6z plus 13. So the coefficient of z squared was 1 and the coefficient of z was minus 6. They're both real numbers. So therefore I can state that if 3 plus 2i is a root, then 3 minus 2i is also a root. But let's say you forget that, okay, and you have to do it in a different manner. Well, if I know that that's a root of it, I know that's your z value, right? So I also know what the factor is. So bring everything across the equals and you'll have the factor. Once you know something is a factor of something, it should divide into it evenly with a remainder of 0. So we're doing long division. Okay, so there was the root. Therefore, this is the factor. Now, I've just brought the 3 plus 2i over the equals all in the one go, so I'm just keeping it in a bracket. It's easier when it comes to long division. So z minus this equals 0 is the factor. I'm now dividing this into the quadratic that they gave. So, z into z squared goes z times, multiply it back. Z by z is z squared, and z multiplied by minus the bracket is just going to be minus the bracket times z. Okay, change your signs. The z squares cancel, they're gone. I'm then left with minus 6z plus the bracket times z. So what I did here was the fact that they both have a z, I'm leaving the z outside the bracket. So I'd be left with minus 6, okay, plus the bracket. So plus 3 plus 2i. And if you tidy that up further, minus 6 plus 3 is minus 3. Okay, so I've now got minus 3 plus 2i times z. And I bring down my 13. Start dividing again. Z goes into this minus 3 plus 2i times. I'll keep it in a bracket up here. I'm now multiplying that bracket back out. So the bracket by z is the bracket times z. And then it's going to be the bracket multiplied by minus that bracket. So just watch your signs. So it's plus the bracket up on top multiplied by the minus times the bracket. Change your signs so that becomes a minus and that plus becomes a minus. So they cancel and I'm left with 13 minus these two brackets multiplied together. So now I'm just working this out, okay, bit by bit. So work out what's inside those square brackets first, split the brackets, multiply it out. I also multiplied that minus into that bracket, so it became minus 3 minus 2i. So split those two brackets and you should get 9 plus 6i minus 4i squared, which ends up becoming 9 minus 4 times minus 1, which is plus 4, and 9 plus 4 is 13. Then it's minus, multiplied by 13 is minus 13. 13 take away 13 is 0, so my remainder is 0. So that's telling me that this factor divided into that quadratic that many times with a remainder of 0. So therefore that's the other factor. So if that's the other factor, they said find the other root. So bring that bracket back over the equals, so it will now become minus the bracket, and multiply the minus into the bracket, so you get 3 minus 2i. So therefore the other root is 3 minus 2i. And also, what have we noted? 3 minus 2i is the conjugate of 3 plus 2i. That was my original root. Z was equal to that. That is Z conjugate. Okay, the next thing we're just going to look at is any type of polynomial that has complex roots. So it's not always just going to be quadratics, okay? So again, if we just kind of revise, the degree of a polynomial is just whatever the highest power of x or the highest power of z is in that particular polynomial. So a degree 3 means the highest power of x was x cubed. Degree 2 means it was a quadratic. Degree 1 means it's linear, and so on and so forth, okay? So if we look at this particular example down here, it says the polynomial f of z, which is 3z cubed, okay, it's hard to see that, but it's 3z cubed minus 5z squared plus 18z plus 12 has n roots. What is the value of n? Well, it's a cubic. So that's telling me if it's a cubic function, it should have 3 roots. They may not necessarily all be real roots, but it will have 3 roots. Okay, so therefore n is 3, and that's because it was a cubic. The highest power of z in that particular example was 3, so therefore it has 3 roots. Okay, and that's all you have to note with that. Okay, now we're going to come back across the conjugate root theorem, which I've already mentioned already. Okay, so all the conjugate root theorem is just stating that when you have a quadratic, or when you have any type of a polynomial, if you are given one of its roots and it's a complex root, if they say, z is a root of this particular polynomial and z happens to be a complex number, well, when you look at the polynomial in itself, if all the coefficients of the z squareds, the z cubes and the z's, if all the coefficients are real numbers in themselves, well then the conjugate root theorem applies. And if z is a root of it, well then z conjugate is also a root. But it's if and only if the coefficients of the polynomial are real numbers. Okay, so for example, if z is 2 plus I, and you're told that this is a root of f of z, the function f of z, well then I can take from that that z conjugate is also a root, but only because the coefficients of the polynomial were all real numbers. Okay, let's look at this example. If 4 plus 3i is a root of this quadratic, well then 4 minus 3i is also a root. Why? Because the coefficient of z squared is 1, which is a real number, and the coefficient of z is minus 8, which is also a real number. However, if you're told that 2 minus 3i is a root of this polynomial, which is 2z squared minus 5iz plus 7, you cannot automatically go by the conjugate root theorem, and you can't just say, right, well, if 2 minus 3i is a root of it, well, then its conjugate is a root of it. You can't. The reason being is because the coefficient of z here, it's not a real number. The coefficient of z happens to be in itself a complex number. So the coefficient of z squared is real, but the coefficient of z is not real. Therefore, the conjugate root theorem doesn't apply here, and you can't automatically say, oh, well, 2 minus 3i is a root, therefore 2 plus 3i is also a root. You can't do it here. So how you would end up getting the other root in this instance is, if you know that this is a root of it, well then you know the factor. And if something is a factor of something, it should long divide into it with a remainder of 0. And that's how you'd get the other factor, and if you have the other factor, then you can turn it into the other root. So that's how you'd have to go with that. So this slide is really, really important, okay? That's the conjugate root theorem. So if all the coefficients within the polynomial are all real numbers, well then the conjugate root theorem applies. And if one complex number is a root of it, its conjugate is also a root as well. Okay, and there is a particular example in 2016 paper 1. There's a question there under the complex numbers question. It's part C, and it's where the conjugate root theorem doesn't apply. Okay, so you could take a look at that. So let's just look at this example. Z is equal to 4 plus 3i, and it is a root of the polynomial. Then so it's telling me that that is a root. Then show that z conjugate, which is 4 minus 3i, is also a root. Well, to show that something is a root of something, it should just sub into it and solve it. So I'm going to sub the conjugate into that quadratic, and it should solve it. Okay, so just watch all your substitution. So you need to square out the bracket, then you're multiplying 8 minus 8 into that bracket and plus your 25. Watch all of your substitution, all your multiplication and all your signs, and remember I squared is minus 1. Things will start to cancel, so you'll see, well, they may not actually no, they don't cancel here, but they add up, and then you eventually, in the last line, they cancel. 41 take 41 is 0. Therefore, z conjugate, which is 4 minus 3i, is a root of f of z as well. Okay, so that is the conjugate root theorem applying there. Okay, so recall, if z is a root of it, then z conjugate is also a root, but if and only if all the coefficients in your polynomial are real numbers. Okay, the next example we're going to go through is to prove the results for z1, z2, z1 and z2 are elements of complex numbers, and a, b, and c are all real numbers. I want to prove the following: that az1 plus bz1 conjugate is equal to az1 conjugate plus bz2 conjugate. So that's the first part I want to prove. The second one I want to prove is that az conjugate is equal to az conjugate. Part 3, az squared conjugate is equal to az squared conjugate. And part 4, z squared conjugate is equal to z conjugate squared. Hence, show that if z1 is a root of that polynomial, well then z1 conjugate is also a root. So that's what I want to do in this example. Okay, so part 1. Well, first of all, they haven't told me what z is, or what z1 is, or z2. So I'm going to label for myself what z, z1 and z2 are going to be for each part of this question. Okay, so I'm going to let z1 be any complex number, alright? So z1 is x1 plus y1i, so that's z1. z2 then is x2 plus y2i. Part 1 wants me to prove that az1 plus bz2 conjugate is equal to that right hand side. So I'm going to work with the left hand side for a moment. Okay, so before I can get the conjugate of something, I need to get what this would be on its own first. So I'm getting az1 plus bz2. A and b are just going to be some real number. Okay, so I am multiplying a by z1 and b by z2. So I'm multiplying into the brackets. Okay, now you want to tidy things up, so you're grouping anything real with real and imaginary with imaginary. So that's why I've underlined the two of these in red, They're both real numbers because there's no i's involved. So I've grouped them together, ax1 plus bx2, and then group the i's together because they're the imaginary part. Alright, so that's the real part, plus I've now just factored I out of both of those terms. So this is the imaginary part, ay1 plus by2i. Okay, so that's what az1 plus bz2 works out to be. And now I want to get the conjugate of that. Okay, so the conjugate of that just means change the sign in front of the imaginary part. So that will now become a minus. Okay, so that's part 1. Part 2, it says to prove that az conjugate is equal to az conjugate. So again, let z equal x plus yi. Okay, just some complex number. So I'm going to work with my left-hand side first. So I want to get az conjugate. Well, the first thing I'm going to have to do is get a by z. So that's a multiplied by z. So multiply into the bracket, you're going to get ax plus ay I. I now want to get the conjugate of that. So it's going to be ax minus ayi. So just change the sign in front of the imaginary part. So that's the left-hand side done. I'm now going to work with the right-hand side. So it's a multiplied by z conjugate. So let's get what z conjugate is. Well, this is z on its own, x plus yi. I now want to get the conjugate of that. So it's x minus yi. I'm now multiplying that by a. So you get ax minus ayi, and that is the same as your left-hand side. So I've now proven part 2. Part 3. Prove az squared conjugate is equal to a by z squared conjugate. Okay, so again, remember z is x plus yi. So work with the left-hand side first. Okay, so it's going to be the conjugate of a by z to be squared. So I need to square out z first. So it's the bracket by the bracket. When you multiply it out, you should get this. X squared plus 2xyi plus y squared I squared. Now remember, I squared is minus 1. So that will end up actually being minus y squared. So I'm now going to group the reals together. So it's going to be x squared minus y squared plus 2xyi. And then all of that was being multiplied by a. So I'm going to do that next. So multiply into it by a. So it's going to be a multiplied by the real part plus a multiplied by the imaginary part, which is 2axyi. Now I'm going to get the conjugate of that. So the conjugate of that means you just change the sign in front of the imaginary part. So it's going to be ax squared minus y squared minus 2axyi. So that's the left-hand side. Now remember what the right-hand side was. That's equal to a times z squared conjugate. So keep the a outside. So we want to get z squared first. Okay, and then we'll get the conjugate of that. So square out the bracket. Bracket by the bracket, you end up with this. Remember, I squared is minus 1. So that becomes minus y squared. Keep the reals together. Keep the imaginary together. So that's plus 2xyi. I now want to get the conjugate of that complex number. So change the sign in front of the imaginary part. So it's going to be x squared minus y squared, that's the real part, minus 2xyi. All of that is then being multiplied by a. So you get a by the real part and a by the imaginary part. And you can see your left-hand side is now the same as your right-hand side. So I've now proven part 3. Sorry, I'm just seeing, am I missing a part there to part 3? No, that was all I was asked, wasn't it? Yeah, prove that a z squared. Yeah, grand, okay. Okay, another way you could have looked at part 3 was in part 2, if I go back to part 2 for a second. In part 2, we had already proven that az conjugate is equal to a by z conjugate. So that was already proven from part 2. So for part 3, when they asked me to prove that az squared conjugate is equal to az squared conjugate, I could have used that as well. So the fact that az conjugate is equal to a times z conjugate is the same then as az squared conjugate equal to a by z squared conjugate. Alright, but again, you probably wouldn't have realised, how would you know that you could have used that? You wouldn't have, so you'd go off and you do the workings like I just did to prove it out. Part 4, prove that z squared conjugate is equal to z conjugate to be squared. Again, remember what z is, x plus yi. So I'm doing out all the workings again. So this is z to be squared, so square it first, you get this. Group your reals with your reals and your imaginaries with your imaginaries. So that's going to be a minus 1 by y squared, which is minus y squared. So I'm grouping the reals together, imaginary together, and now I'm going to get the conjugate of that, which means I change that to a minus. That's your left-hand side. Let's look at the right-hand side. I'm trying to prove z conjugate to be squared. Well, this was z, okay? I want to get the conjugate of z, which is x minus yi. I then want to square that, split the brackets, multiply it out, change that to a minus 1, and group your reals with reals, imaginary with imaginary. Your left-hand side is equal to your right-hand side. So I've now proven that z squared conjugate is equal to z conjugate to be squared. Now, there's a hence part. It said hence, show that if z1 is a root of this polynomial az squared plus bz plus c, then z1 conjugate is also a root. You are now going to use all the previous parts that you've just done in part 1, 2, 3, and 4 to do this hence part. Okay? So, f of z is az squared plus bz plus c. They have said if z1 is a root of it, well, if it's a root of it, it should sub into it and solve it. So that's what I'm doing next. F of z1 will now look like this. az1 squared plus bz1 plus c, and that should equal 0 now. It wants me to prove that z1 conjugate is also a root of it. So, there's no point in me just subbing in the conjugate of z1 into that as a complex number format, like x plus yi. There's no point in doing that, because that's not actually going to help, because I don't know what the actual conjugate is, bar being in general terms. So what we're going to do is we're going to apply all the knowledge we've just proven from parts 1 to 4, and we're going to get it out that way instead. So, I now know that z1 is a root of it, so I've subbed into it here. Next thing, I'm going to get the conjugate of the left-hand side should equal the conjugate of the right-hand side. Okay, so I've done that. I'm now going to break it up. So what I learned from part 1, if you look back at part 1, and I'm going to flick back to part 1. From part 1, we already proved that the conjugate of az1 plus bz2 can be written as the separation of both of them. Okay, we already proved that. So I'm going to use that knowledge now for the first line of part 4's hence. So the conjugate of all of that, I can just separate it out. It's az1 squared conjugate plus bz1 conjugate plus c conjugate is equal to 0 conjugate. Now, c is just a constant, and so is 0. So if you get the conjugate of both of them, they're just the same numbers. Okay? Now, to go from this line to the next line, I'm going to use parts 2 and 3. So in parts 2, if you look back to your part 2, I'm not going to keep flicking over and back. You can look back to it yourself. I have already proven that az1 squared conjugate, I've already proven that that can be written as a times z1 squared conjugate on its own. I've already proven that bz1 conjugate can be written as b times z1 conjugate. And the conjugate of c is c, and the conjugate of 0 is 0. That's from parts 2 and 3. Now, from part 4, I'm getting out the next line. So I can write that z1 squared conjugate is the same as z conjugate to be squared. That's from part 4. So a z1 conjugate squared plus b, that doesn't change, they're the same thing, plus c is equal to 0. So what I've now done is z1 conjugate is obviously a root of the original function, because look, they were subbed into it. Like what I did when I just subbed in z1 on its own, right? This was proving that z1 was a root of it by just subbing it in like that, equaling it to 0. And I've now managed, from using parts 1 to 4 of the entire proof, I was able to show that z1 conjugate is also a root of the function. Okay, this isn't a formal proof or anything, it's just using your knowledge of substitution really, okay, and complex numbers. Okay, the next example, you're given the polynomial f of z, which is 3z cubed minus 5z squared plus 13z plus 5, and it has n roots. So what is the value of n? Well, if it's a cubic, that means there are 3 roots, so n is 3. If 1 plus 2i is a root of it, find the other root, or find another root, right? Well, first of all, this is a complex number. If they're saying that that's a root of that, let's see. 3 is real, minus 5 is real, 13 is real. So that means the conjugate root theorem applies. So if 1 plus 2i is a root of that, well then its conjugate, which is 1 minus 2i, is also a root of it. Okay. Then it says explain why f of z must have a real root. Well, from part 1 we've already come to the realization that that function has 3 roots because n is 3. Okay, it has 3 roots, it's a cubic. So far I know that's one root, I know the conjugate is another root. Well, it must have a third root. Well, the third root would have to be real in order for you to have 3 roots that will multiply together to give you back that cubic function. So 2 are complex and 1 is real. Part 4, it wants me to find the other real root. Okay, again, this is coming from when we did normal algebra. Okay, if I know two roots of a cubic, I can get the two factors. Okay, so if I know the two factors, I can multiply the factors together, and that would give me a quadratic. That's telling me then the quadratic is also a factor of that cubic, so it should divide into it. And if you divide a quadratic into a cubic, you should get back a linear. Alright, so that's what we're going to do here in this part 4. Okay, so again, these are just the answers written out to parts 1, 2, and 3. Okay, A, B, C, and D are the coefficients up here. They're all real numbers. Okay, so I'm now going to move on to part 4. Okay, so and I'm going to use, it doesn't really matter which method you want to use, method 1 or method 2. Okay, so we know that 1 plus 2i is one of the roots, and its conjugate, 1 minus 2i, is the other root. Okay, we can use this method, x squared or z squared even, minus the sum of the roots times z plus the product of the roots is equal to 0. So you can go with method 1 if you want. Alright, so the sum of the roots, if you add those two roots together, you get out a 2. And then if you multiply the two roots together, split the brackets, you get a 5. So the quadratic ends up being z squared minus 2z plus 5. So that quadratic came from the two complex roots. So that means if those were two roots and we got their factors, this quadratic is also a factor of the cubic. And we would do long division. Okay. Alternatively, you can go off and do the method that I usually do, which is multiply the two factors together, split the brackets, multiply it all out. You'll still get that same quadratic, so it makes no difference which method you go with. Okay, so I am now going to divide that into that. Okay, so that quadratic is a factor of the cubic, so it should divide into it evenly with a remainder of 0, and we'll get the other final root. This is just going through the second method of getting the quadratic. Okay, right, so set up your long division. Z squared minus 2z plus 5 should divide into that cubic expression. So z squared into 3z cubed goes 3z times. Multiply it back out. 3z by z squared is 3z cubed. 3z by minus 2z is minus 6z squared. 3z by 5 is 15z. Change all your signs. You can see that in red I have changed them. The z cubes cancel. Minus 5z squared plus 6z is z squared. Plus 13z minus 15z is minus 2z. And plus 5 and nothing is plus 5. Start your division again. Z squared divides into z squared plus once. Multiply it back out. 1 by z squared is z squared. 1 by minus 2z is minus 2z. And 1 by 1 by 5 is 5. Change your signs in red. They all cancel and you get a 0. Therefore, that quadratic divided into that cubic this many times with a remainder of 0. That means that's the other factor. So 3z, because this was one of the factors, the quadratic was a factor of that, so that's the other factor, it's linear. 3z plus 1 is a factor. So if that's a factor, let it equal 0 and solve for z. So 3z plus 1 is equal to 0. Bring over the 1, and it's now 3z equals minus 1, and then divide across by 3. You'll get z is equal to minus 1/3. And that is a real number. So 2 of the roots were complex numbers, and this is a real number. Okay, so this is a real root, minus 1/3. Okay, so in your book, go to exercise 12.7, which is on page 300. Okay, and I want you to do question 2. Okay, so question 2. Question 4. Question 8. Question 9. Question 10. Question 12. Question 14. Then pause the video and come back and look at the solutions. Okay, question 2. f of z is that quadratic polynomial. Verify that minus 3 minus 4i is a root. So it should sub into it and solve it. Okay, so when you sub into it, you should get out a 0. There's all your multiplication. Part 2, write down the other root. Well, if I've now proven that minus 3 minus 4i is a root of the original quadratic, look at the original quadratic. All the coefficients of the z's and the z squares, they're all real numbers, so therefore the conjugate root theorem applies, which means that minus 3 plus 4i is also a root. Okay, so the other root is minus 3 plus 4i. Question 4. Show that z equal to minus 1 is a root of that equation. Well, if it's a root of it, it should sub into it and solve it. So you're subbing in minus 1 and you get out 0 equals 0. So therefore minus 1 is a root. Then it says show that the other two roots are complex. Right, well if you know that z equal to minus 1 is a root, then you know the factor of z plus 1 should divide into it evenly with a remainder of 0. So I'm now going to divide z plus 1 into it. Okay, so just watch all of your division. So dividing in z plus 1 into that cubic expression, you should get a remainder of 0. So therefore z plus 1 divided into the cubic, z squared minus 6z plus 10 times. So that's the other factor. But the question said find the other two complex roots. So I now need to go off and solve that quadratic. So use your minus b formula. And you should get out 3 plus or minus 1i. So they're the other two complex roots. So one of the roots was real, it was minus 1, and the other two complex roots are 3 plus or minus I. Question 8. Okay, so you were given this graph. Part of the graph of f of z is z cubed minus 11z minus k as shown. The coordinates of x and y intercepts are a0 and 0b, where a and b are integers, and write down the value of b and a. So pick out points on the graph.